Hey everyone, and welcome. Today we are diving deep into a really fundamental concept in physics, the uniform electric field. Now, this is basically an invisible force that can do some amazing things, like accelerate particles to mind-boggling speeds. And by the end of this, you'll know exactly how it all works. Okay, let's get into it. So, it all starts with something that looks pretty simple. Two parallel plates. One's got a positive charge, the other's negative. And right there, in the space between them, is this perfectly consistent, uniform field of force. You can't see it, you can't touch it, but trust me, its effects are super powerful, and what's really cool, they're predictable. And that, of course, leads us to the big questions, right? How do we actually describe this field with math? And what in the world happens when we shoot a tiny charged particle, say an electron, right through the middle of it? What kind of path is it going to take? So here's our game plan. We'll start with the basics, what the field actually is. Then we're going to explore the two main paths a particle can take when it zips through it. After we've got the physics down, we'll run through some exam-style questions to make sure everything really sticks. First up, let's build our foundation. We're going to define what makes a field uniform and get our hands on the one key formula that you absolutely have to have in your physics toolkit. So what do we mean by uniform? Well, it's pretty much what it sounds like. It's a field where the electric strength is the exact same at every single point. If you were to draw it, the force lines would be perfectly parallel, evenly spaced, and always pointing away from the positive plate toward the negative one. This means a charged particle feels the exact same amount of push or pull no matter where it is inside that field. Pretty neat, huh?
Okay, now this is where it gets cool. How do we get our main equation? We don't just pull it out of thin air. We start with some physics basics you already know. Work is force times distance. We also know that the electric field, E, is just force per charge. And the potential difference, V, is work per charge. Now, if we just do a little bit of rearranging and substitute these ideas into each other, boom, we get E equals V over D. A beautifully simple and super powerful formula.
All right, time to put that shiny new formula to the test. Here's the classic problem. We've got our two plates, we know the voltage between them, and we know how far apart they are. So how strong is that electric field? Let's break it down. First step, always, is to figure out what we know. Voltage, V, is 1,000 volts. Easy. The distance, D, is 5 centimeters. But hold on. Physics needs standard units, so we've got to convert that to 0.05 meters. Always watch out for that. Now, we just plug them into our formula. E equals 1,000 divided by 0.05. And the answer is 2.0 times 10 to the 4 volts per meter. Just like that. So now that we've got a handle on the field itself, let's get to the really exciting part. What happens when we actually throw a charged particle into the mix? It turns out there are two main ways this can go down. And this visual shows the two scenarios perfectly. On the left, you see what happens when a particle just gets released inside the field. It moves parallel to the field lines, straight across. But now look at the right. This is what happens when a particle already has some sideways speed when it enters. It gets pulled into a curve. And this really sums it up. Parallel motion is like a drag race. It's just pure straight-line acceleration because the force is pulling it in the exact direction it's moving. But perpendicular motion, that's more like a curveball. The particle wants to go forward, but the field is constantly tugging it sideways or downwards. The result is that awesome parabolic arc, just like a ball thrown through the air. So let's dig into that first case, the drag race. This is all about a particle just getting yanked across the field in a perfectly straight line. Okay, here's a perfect example. We've got an alpha particle, which is basically just the nucleus of a helium atom. We know its mass, we know its charge, and it's starting from a dead stop at the positive plate. The mission, should you choose to accept it, is to find the force on it, its acceleration, and how fast it's going right before it slams into the other plate. All right, let's walk through this chain reaction. For part A, the force is just charge times the electric field, which is V over D. We plug in the numbers and get a tiny force, 1.28 times 10 to the minus 14 newtons. Now for part B, we just use good old Newton's second law. Acceleration is force over mass. Using the force we just found, we get a frankly insane acceleration of 1.91 times 10 to the 12 meters per second squared. Wow. Finally, for part C, we grab a kinematics equation. V squared equals U squared plus 2AS. Since it started from rest, U is 0. We solve for V and we get a final speed of 240,000 meters per second. See? Each step just feeds right into the next one. All right, time to tackle the curveball. This is where a particle flies into the field with some sideways speed. Things get a little more complex here, but the physics is just as elegant. Now, the secret weapon for solving these kinds of problems is a classic physics trick. Split the motion into two separate, independent parts. Horizontally, in the x direction, there's no force, so the particle just cruises along at a nice constant speed. But vertically, in the y direction, that electric field is pulling on it the whole time, giving it a constant acceleration. And here's the genius part. The time it spends cruising sideways is the exact same time it spends getting pulled downwards. If we can just figure out that time, we can solve the whole thing.
So, let's put it all together now. We're going to walk through a complete problem that uses every single one of those perpendicular motion ideas we just talked about. Here we go. An electron zips into a field. We know its horizontal speed, we know the field strength, and we know how long the plates are. The big question is, how far does it get pulled off course vertically by the time it comes out the other side?
Okay, let's trace the steps, because this is where it all connects. First, find the vertical force on the electron with F equals QE. Then, find its vertical acceleration using A equals F over m. Now, for the crucial link, we use the horizontal motion to find out how long the electron is actually between the plates. Since its horizontal speed is constant, time is just the length of the plates divided by that speed. That gives us a ridiculously small fraction of a second. Finally, we take that time and plug it into our displacement formula, y equals 1/2 at squared. The result? A vertical deflection of 5.48 millimeters.
You've seen the theory, you've seen the examples, now it's time to run the gauntlets. This is a lightning round of exam-style questions to really make sure this is all locked in. You ready?
First up, what is an electric field line? It's the line showing the direction of the field at any point. So if a field is stronger at point Y than at point X, how do the lines look? Yep, they'd be packed closer together at Y. Okay, question 2. How would you actually measure the field strength? Simple. You'd put a tiny test charge in there, measure the force on it, and then just calculate force divided by charge.
Question 3. That particle entering at a right angle. Describe its motion. You got this one. It follows that parabolic path, our curveball. And why? Well, that's question 4. The field accelerates it by exerting a constant force, which means constant acceleration. And that just keeps pumping up the particle's kinetic energy and its speed. Last one. What happens if you dial down the electric field strength? What does that do to the particle? Well, it's a domino effect, really. A weaker field means less force. Less force means smaller acceleration. And smaller acceleration means the particle gets deflected a lot less. Everything's connected. So there you have it. From the old school TVs with cathode ray tubes to the giant particle accelerators scientists use today, this principle is absolutely everywhere. Which leaves us with a final thought. We now have the ability to steer tiny, tiny particles with incredible precision. Just think about it. What kind of future technologies could that unlock? The possibilities are pretty mind-blowing. Thanks for joining me.